Okay, so chapter 20 is on sound. So first of all, sound is a form of energy that exists whether or not it is heard. If a tree falls in the forest, well, then there will be all this snapping and releasing of energy, and that will send sound waves out into the environment, whether or not anyone is there to hear it. So sound waves are produced by the vibrations of matter. For example, in a piano, a violin, or a guitar, the sound is produced by a vibrating string. In a saxophone, there's a vibrating reed. In a flute, there's a fluttering column of air at the mouthpiece. And in my voice, my vocal cords are vibrating. Normally, there's the original vibration stimulates the vibration of something that's larger or more massive. For example, on this violin, the original vibration is the string, but then this wooden sounding board also vibrates and is what produces most of the sound. The air column in a reed or wind instrument also is the more massive thing that vibrates. The air in your throat of the mouth of a singer vibrates as a result of the original vibrations of the vocal cords. So this vibrating material then sends the disturbance through the surrounding medium, like the air, in the form of longitudinal sound waves. So the frequency of the sound wave is the same as the frequency of the vibrating source, and our impression of the frequency is called pitch. So, for example, this piano has lots of different keys, and each key has a different pitch. So there's a C, you go lower and lower and lower pitch, a lower frequency, that's called lower pitch. And the lowest note on the piano is this A, which has a frequency of 27.5 hertz. The highest note on the piano has a frequency of 4,186 hertz. And our ears can hear in the range from about 20 hertz up to 20,000 hertz. And as we grow older, this limit decreases. So sound waves with frequencies below 20 hertz are called infrasonic or infrasound, and sound waves with frequencies above 20,000 hertz are ultrasonic or called ultrasound. And humans cannot hear infrasound or ultrasound. Although giraffes can hear frequencies in the infrasound below 20 hertz, and dogs, we know, can hear sounds with frequencies above 20,000 hertz, so ultrasound. So sound waves are vibrations that are made of compressions and rarefactions. In a compression region, the density and pressure are slightly greater, so if you open the door in this room, it'll compress the air. And in a rarefaction, the density and pressure are slightly lower than the average. And so if you slam the door, there'll be a rarefaction wave which will travel out and pull the curtain inwards. The wavelength of sound is the distance between adjacent compressions or rarefactions. So there it is. As these two compressions go by, the distance between them is called the wavelength. So here's how sound is heard. First, you need a source, such as this loudspeaker has a paper cone that's vibrating. That pushes and pulls the air molecules next to the loudspeaker and sets them into motion. And that produces compressions and rarefactions which travel outward through the air. And then it hits a detector, such as your eardrum or a microphone, which sets up a vibration in the detector. And for example, in this microphone, that produces an electric current, which we can then record in our computers. Sound doesn't just travel through air, it can also travel through liquids or solids. In a liquid or solid, the atoms are closer together, so the speed of sound is greater. It's about 4 times greater in water than it is in air, and 15 times greater in steel than it is in air, which is why sometimes you can hear a train coming before you can hear it with your ears. You can hear it by listening down at the rail. The speed of sound in air depends on temperature, pressure, and humidity, but it's about 330 meters per second. And we know that it tends to rise by about half a meter per second per degree of Celsius. But one of the consequences of this is that Light, which travels at 300,000 kilometers per second, travels almost instantaneously. So if there's a bolt of lightning, you see it before you hear it. And if you actually count the seconds between when you see it, which is instantaneous, and when you hear it, and you divide by 3, that'll give you the approximate distance to the source in kilometers. It's a third of a kilometer per second. So sound can be reflected off of walls. This is called echoes or reverberations. And sound can also be refracted. So if you have warm air below and cool air above, the sound will travel faster through the warm air. It can actually bend the waves upwards. If it's reversed, it can bend the waves downwards. And reflections and rarefactions will happen inside solid and liquids, like inside your body. And so there's something called ultrasonic imaging, which is when a device sends high-frequency sounds into the body and records the reflected waves that are produced from organs and other bones and things inside your body. So this is an alternative to using X-rays. You can just send sound waves, and this was sent into my wife in early 2011, and we saw an image of my daughter before she was born. So every object, it turns out, has some natural frequency that it wants to vibrate on. This depends on the elasticity of the object, the mass of the object, its shape, and its size. So, for example, these tuning forks, if you hit any one of them with a hammer, they'll vibrate at some natural frequency. There's also something called forced vibrations. So if you have a motor, like some machinery or a paint shaker or something, you can force oscillations to happen at any frequency that you want. And resonance is the phenomena in which the frequency of the forced vibrations matches the object's natural vibration frequency. An example here is 2 identical tuning forks. If one of them is already shaking, you can set up sympathetic vibrations in another tuning fork that's nearby. And this is a phenomenon of resonance. It's because this frequency is matched to the natural frequency of this tuning fork. Another example, if you're pushing a swing, and you push with the same frequency as the natural frequency of the swing, then the amplitude increases. If your radio is tuned to the right frequency, you can pick up on a particular radio station. Also, when troops, if they're marching at a certain rhythm, and that matches the rhythm of a bridge, you can actually destroy the bridge by marching over, which is why troops are not allowed to march in rhythm when they go over a bridge. It's just to go out of step. Here's an example of exactly something like that happening. Back in 1940, there was a suspension bridge going over the Tacoma Narrows, and the way the wind went through these narrows set up a forced vibration, which matched the resonance frequency of this bridge, unfortunately. And so what eventually happened is it collapsed the bridge about 6 months after it was first built. Quite dramatic. So interference. We learned about this a little bit in the previous chapter, but if you have 2 waves that are in phase, they produce a wave that has an increased amplitude. This is true for longitudinal waves as well. If these 2 waves are in phase, so the compressions match the compressions, rarefactions match the rarefactions, then you get a wave with increased intensity. However, if waves are out of phase, they'll cancel each other out, and you can just get a zero amplitude wave. And this is true as well with longitudinal waves. If the compressions match the rarefactions in this wave, and the compressions match the rarefactions in this wave, they can cancel each other out and get zero sound. So there's something called sound canceling headphones that actually have microphones inside the headphones that listen to the surrounding sound and produce mirror image wave patterns that are fed into your ear so that it cancels the sound out. So you can be in a noisy airplane and get some peace and quiet. And finally, there's beats. So if you have 2 waves of similar but not equal frequencies and you superpose them, you can get this phenomenon of beating, where the sound that's produced gets loud because it constructive interference, and then later quiet because of destructive interference, and then loud again, and then quiet again. And this has an application when you're tuning pianos. If you have a known frequency source, like a tuning fork or something, and you play it at the same time as a piano key, and you hear beats, then you know that the frequency is not quite the same. And if you make those beats go away, then the frequency is the same. And you can do the same thing if you're tuning an orchestra to a piano tone. You're listening for the beats, and you're trying to make them get slower and go away.